Hi everyone, this is the video lesson for 4.5, an algorithm for curve sketching. Here's the warm-up. Number 1, how do we calculate the following? To find a domain, you're really looking for the possible values of x. Now, of course, sometimes there'll be a vertical asymptote, which we'll get to in part C. And if there is a vertical asymptote, just make sure that that is included into the domain. So, for example, let's say there's a function, x cannot equal to 1. So you put that in the domain because the vertical asymptote is at x equal to 1. So just be mindful. Of course, there are other cases which we'll cover as we go through the examples. Part B, to find the intercepts, there are two cases. To find the x-intercept, you have to set y to be 0, and you got to solve for x. Likewise, to find the y-intercept, you have to set x to be 0, and you solve for y. Now, if you look at part C, asymptotes, the first type are called vertical asymptotes, which looks something like that. You're basically looking for the restriction or restrictions. It depends on what you have as the function. So again, whatever x cannot be, that becomes the vertical asymptote. Now likewise, to find the horizontal asymptote and the oblique asymptote, let's give you a function. So, for example, if there's a function with ax to the power of m plus some other terms divided by b times x to the n plus some other terms, here's how you break it down to the three corresponding cases. If the exponent at the top is smaller than the bottom, and this could be 1 smaller, 2 smaller, as long as the exponent at the top, and again by exponent I really mean the degree, which is the largest exponent, then there is a horizontal asymptote located at y equal to 0. In the second case, again this we've talked about in the past, but if m and n are the same, then there is a horizontal asymptote for y equal to a over b. Now the moment you find the horizontal asymptote, this implies there's no oblique. Likewise, if you find the oblique asymptote, this implies there will be no horizontal asymptote. On the other hand, if you cannot find the horizontal asymptote, this tells you nothing about the oblique asymptote and vice versa. Now, here's the next part. If the exponent at the top is exactly 1 larger than the bottom, then you would have to divide. And of course, this you did back in MHF. You can divide using long division or the shortcut synthetic. It's really up to you. But once you find the quotient, which is in the form of y equal to ax plus b, maybe I should write down a. Let's write down mx plus b, so you're not confused with the a as the coefficient. That becomes the oblique asymptote. Critical points. To find critical points, there are two cases. First, you find the derivative and you set it to 0 and you solve for x. Or sometimes you find the derivative and you got to figure out what happens to the denominator that would make it either undefined or does not exist. Maybe I'll put this in quotation marks. And those values become critical points. So again, you find the derivative, you set it to 0 and you solve for x. Or, if it's a fraction, look for the denominator. And you have to be mindful because sometimes the restriction for the denominator, they're simply vertical asymptotes, or they're actual critical points. And again, it depends on the function. Now, part E, interval of increase and decrease. So again, we drew this diagram, which I'm going to draw again at the end for you. It's going to be very useful. So, IOI, or increase, or IOD, I'll just write down decrease. These are the cases in terms of what it looks like. But in terms of finding it, to find the interval of increase, you basically find all the cases where the derivative is going to be positive. Now, on the other hand, if the derivative is going to be negative, that's for the interval of decrease. Part F, points of inflection. When you set the second derivative to be 0 and you solve for x, those are your inflection points or points of inflection. Or if you look at the second derivative and you find all the cases where the function will be undefined or does not exist, again, I'll put them in quotation marks, they, again, may be vertical asymptotes or the actual points which are points of inflection. G, concavity. So again, there are two cases when it comes to concavity. We did this from before. I'm going to compose this in one big table in a moment. But if a function is concave up, it's going to look either one of those three cases. And on the other hand, if it's going to be concave down, it will look something like that. And again, to solve this, if it's concave up, that just means the second derivative is positive. And likewise, if you want to find out when the function is concave down, you take the second derivative and make sure that is negative. And of course, you can kind of relate this to the next part, which is max and min. So to find the max and min, of course, you can go through the first derivative test or the second derivative test. So for a maximum, here's the two general ideas. You can say, okay, a maximum occurs when the function is increasing, it hits a point, and it starts to decrease. And you have to be clear, I always draw this concave down graph, and that's not the only case. Because I'm drawing concave down only because I'm telling you that f double prime of x, or c, which is the critical value, this must be negative. So if you plug in x, where x is the critical point, or you can say c for critical point, if you plug it into the second derivative and it's negative, that means it's concave down, which means it must be a maximum, right? And the first derivative test is when you look at increase and decrease, and that point must be a maximum. Now again, if you look at a minimum in a similar way, you can say the function is decreasing, then it starts to increase. And that's the first derivative test. Or you can look at the second derivative, plug in the critical point, and it's going to be concave up. So again, really important, you think about this before we explore examples 1 and 2. Now, let's give you a couple more bonus ideas. This is extremely, extremely important. If you want to be able to graph virtually anything from your textbook and your homework and in this course, this is the one graph you have to memorize or at least understand really, really, really well. So if you think about this, and we did this in the previous lesson, this is the combination of increase, decrease, and concavity. I'll put this in a different color. So if the function is increasing and is concave up, it's going to look like that. If the function is decreasing and is concave up, it's going to look like that. If the function is increasing and concave down, it's going to look like that. And of course, if the function is decreasing and concave down, it's going to look like that. And again, just to circle back to the beginning of this, one idea that I strongly recommend is you graph as you go. So graph as you go. Do not graph everything at the end. And there's nothing wrong with that, by the way. I mean, a lot of people do successfully by graphing it at the end. But if you want to minimize the mistakes, it's hard to figure out where the mistake is if you go through 10 different steps and then graphing your outcome at the very end. By graphing as you go, you can pick up the mistakes if they're in disagreement. So make sure you understand this, and I will continue in part 2 with example number 1. I hope this makes sense.